All right, today we're going to continue our study of electricity, charge, electric fields, and talk about something called electric potential. And electric potential or electric potential difference is also referred to as voltage. So that is a term you probably are familiar with, even if you haven't studied electricity before. Let's take a look at our objectives here for today. First is define electric potential difference. And calculate potential difference from the work required to move a charge. Okay, so we're going to see some connections here, some analogies between a topic we had earlier in the semester with gravitational potential energy and the fact that we could change that energy by doing work to the system. So that same concept we're going to apply here as we start to understand and explore electric potential. All right, so here we are, gravitational potential energy, right? This is the potential energy due to position, right? The higher we lift an object up against a gravitational force, the greater its potential energy. So if we had a mass hanging from a string here, and we pull on that string and lift it up to this top position, that would have high potential energy compared to the mass sitting on the floor, right? That would be low potential energy. Now, if we just let gravity fall and pull that mass back down to the floor, it has gone from a high level of potential energy to a low level of potential energy. So in a sense, we could say negative work is being done by gravity because it's reducing the energy of the system, okay? So in this case, gravity's doing the work, but it's kind of negative work because we're losing energy here. Now, what if we do the opposite, right? We start from a position of low potential energy and we pull on the rope and raise it up to a position of high potential energy. Here, the work is being done from an external standpoint, right? You or somebody had to pull on that rope to actually increase the potential energy of the object. So in this case, we would say there's external work or positive work being done by that external force, okay? So when we lose potential energy, we say negative work is occurring on the system. And if we increase, then it's positive work being done and it's by an external force. All right, so keep those concepts in mind here. We're now going to apply those to a charge in an electric field. So we talked about this in the last lesson, right, with electric fields. Where would the potential energy be the greatest? Now we have our red object, right, that's creating the electric field. And think of the small black charge as our test charge. Remember, we measure electric fields by putting an arbitrarily small electrical charge, positive charge in the field, and then seeing what forces act on it, right? What direction would those forces be? So which location, A or B, would have that test charge at its greatest potential energy? Well, if we were to let go of that charge, right? Let's say we're holding on to it at position A and then I let go of it, it's going to move to position B, right? Why is it going to move to position B? Well, two ways to think about it. One, we had two positive charges and they're going to repel each other, right? So that's what's going to cause it to move from A to B or move away from the positive red charge, the big Q. Another way to think about it is when you put a positive charge in an electric field, it's going to create a force on that that is in the same direction as the electric field. So that force moved it again from A to B. And let's say we move it a distance of D, okay? So in this example, the test charge has gone from a position of high potential energy at the A location to low potential energy at the B location. Now notice we didn't have to do any external work to let that test charge move. We just let go of it and it moved to its lower potential energy. In the same way, we just let go of that mass and it fell back to the ground and it reduced its potential energy. So in this case, the potential energy of the test charge decreases. We would say negative work was done on the test charge. Now let's look at the other situation, right? We're starting at location B and we want to move that object to location A. Now here, we're moving it against the electric field direction. So it's going to require an external force to move it, right, from a low potential energy position at B to a high potential energy position at A. So in this case, we would say external work is required to move the test charge against the electric field, and the potential energy of the test charge has been increased. Okay, so hopefully you're seeing the analogy here, right, between gravitational potential energy and in this case, electric potential energy. So let's just see if we have the right understanding here of these concepts. I'm going to show you a charge in a uniform electric field, right? It's uniform because all the lines are equally spaced here. And I am going to ask some questions. And so in this first one, what if we move the test charge from point A to point B? So can we answer these three questions? Is there external work done on the test charge to move it from point A to B? Does the potential energy increase or decrease? In other words, is it greatest at point A or point B? And the electric potential, is that greatest at point A or B? So let's do this together. Now notice if we move it from A to B, we're moving with the electric field, same direction as the electric field. So that's the natural direction that it wants to move, right? If we move it to this point here, we would say, no, there's no external work being done. All we'd have to do is let go of that test charge and it would want to move towards the location B. So where would the potential energy be greatest? Well, it would have been at A where we started, right? And wherever the potential energy is greatest, the electric potential is also the greatest, okay? These two answers will always be the same. All right, let's try a couple more, see if you can figure these out yourself. So just pause the video, see if you can answer these questions. Okay, here we go. Now we want to move it from A to B. We're moving it against the electric field. So yes, we're going to have to do external work. Where would the potential energy be greatest? Well, since we're doing work to that charge, we're increasing its potential energy. So it's going to be greater at B, and then the electric potential, therefore, will also be greatest at B. All right, here's another one. External work? No, we're moving with the electric field. So the greatest potential energy was at point A where we started, and the greatest electric potential also at point A. All right, last one here. We want to go down in this case. So we're going against the electric field, right? So yes, we're doing external work to move the test charge, and the greatest potential energy will be where we've moved it to, at location B, and therefore electric potential will be greatest at location B. All right, so we have the concept here of how do we change a charged object's electric potential, right? By moving it within an electric field. Now let's get into the math here a little bit. The difference in electric potential is the ratio of the work needed to move a charge to the amount of that charge. Okay, so let's say we have this test charge Q, right? Little q, the black object, and we want to move it a certain distance through an electric field. Now, we're going to do positive work on it. Let's look at that case, right? We're going to move it from point B to A against the electric field. We're going to be increasing its potential energy, and we're going to be increasing its electric potential difference, okay? So how do we do that? It's the work divided by the charge itself. Now, the work, remember, is equivalent to energy. The units are in joules. So we move that up, right? And remember, how do we calculate work? Well, we'll get to that in a second. Let's just remember Q is the charge in coulombs of the test charge. And then what that gives us is the electric potential difference in joules per coulomb. And the unit then the other name we have for that unit, joules per coulomb, is called a volt. Okay, so the change and we use the symbol V for electric potential difference. The change in the electric potential difference is equal to the work done on the charge divided by the amount of charge that it has. Now, remember, how do we define work? Well, it's force times distance, back from the first semester. So let's plug that in, right? The force times the distance divided by the charge Q. Now, force divided by the charge, does that look familiar? Remember, that is our formula for calculating the electric field strength. So we can replace F over Q with E, electric field strength, and the change in electric potential simply becomes the electric field strength times the distance that we're moving the charge in that electric field. Okay, so there it is. Electric potential difference is equal to the product of the electric field strength and the distance moved by the charge. So here's the official definition: electric potential difference. Two ways to think about it, right? The field strength times the distance that we moved it, or the work done on the charge divided by the amount of charge on that object that we're moving. Electric field strength is in newtons per coulomb, distance is in meters, and we get this unit called a volt that's equal to a Newton per coulomb times the distance in. Okay, but the units are kind of messy. That's why we've given it this new name called a volt. All right, let's look at an example here. See if we can apply the math here a little bit. It says two charged parallel plates are 1.5 centimeter apart. The magnitude of the electric field between the plates is 1800 newtons per coulomb. So we want to do two things. What is the electric potential difference between the two plates, between the positive plate on the top and the negative plate on the bottom? And what work is required to move a proton from the negative to the positive plate, right? We'll be moving it against the electric field. It's going to require external work. All right, so let's label some information here. It says 1.5 centimeters. Let's convert that to 0.015 meters. And we're given the electric field strength of 1800 newtons per coulomb. So the first one is, what's the electric potential between the plates? Well, we just need to multiply the electric field strength times the distance. So if we do that, right, we wind up with this measure of 27 volts. 27 volts would be the electric potential difference between that top plate and the bottom plate. We can now also solve for the work, right? Now that we know the electric potential difference, we can rearrange this. So we solve for the work, and we're going to multiply the voltage, 27 volts, times the charge on the test charge. So remember, this is our elementary charge. This is a charge of a single proton. Okay, so if we calculate that, we'll see that this is a very, very small amount of work. It doesn't take much work to move a single proton through this electric field, 4.3 times 10 to the negative 18th joules. All right, so you've heard of the term voltage before, right? And maybe the most common application of it is in batteries, right? You think of a battery in your car. Those are rated at nominally 12 volts. They're actually like 13.2 fully charged, but we normally talk about it being a 12 volt system. But the role of the battery is to supply energy to whatever it's connected to. Now, these are like the big D cells. When we're back together in class, in return to school, we'll have a chance to play around with some of these circuits. So basically the battery is going to pump, think of it as a pump that pumps the charge from the negative plate or terminal to the positive terminal. And as it does that, it's going to raise the potential energy of the charge, and it maintains an electric potential difference across whatever it's connected to. Okay, now let's look at an example, right? Here's our battery down below in red. Think of it as our charge pump, and we've connected a light bulb to it, right? That's what's going to use the energy in the battery. Okay. The internal circuit is what's going on in the battery, right? That's a chemical process that can be reversed, right? We recharge up the battery, but we use the chemical energy and convert that into electric potential energy. Externally, the light bulb is going to consume the energy. In other words, we're going to lose energy as the electrons travel through the light bulb, cause it to heat up, cause it to produce light. So basically we're doing work on those external circuits, and the output of that work in this case is light. Now, let's take a path around that circuit, starting with the positive terminal of the battery, and see what happens to the electric potential as we travel or through that circuit. Now, a circuit is just simply, think of the name, it has this kind of word circle in it, right? So a circuit has to have a complete loop, right, for the electrons to travel. So we're going to follow through the different parts of that loop. Starting at point A, right, we're at the positive end of the battery, which is 1.5 volts. Now, if we move from A to B, will we lose any electric potential? Well, if we have a good conductor, a good copper wire, for example, that connects points A and B together, we should have minimal loss of energy. So if you look at this diagram on the right here, we move from point A to B with no change in the electric potential. Notice we're just moving horizontally at that 1.5 volt level. Now we move through the light bulb, that's where we're going to lose our energy, right? We're going to do work on that light bulb, use up the electric potential energy in our charge and our electrons that are flowing through here. And we're going to use all of that up so that the full 1.5 volts will be lost or reduced when we go from point B to point C, right, through that light bulb. So if you look at our diagram here, you can see we now drop down to 0 volts. And then we have that same good copper wire that connects point C and D together with the negative terminal of the battery. So we wouldn't expect to lose any voltage there. And really, we have no voltage left to lose, right? We're back down to 0. And then what happens to the charge, right? The charge goes back into the battery, and the battery pumps it up or increases its electric potential back up to 1.5 volts again. And it's ready to go through the circuit and do more work on our light bulb. Okay, so this is a way for us to kind of model what's happening with the electric potential in a circuit that includes a battery, right, which supplies our energy, and then an external circuit where that energy is used to do work. Here's another example here, a little more complicated, right? We've got a 6-volt battery and we've got 3 identical light bulbs. Okay, so what would that look like? See if you could sketch that out. Pause the video. Okay, here we go. So from point A to B, right, we've got a good conductor wire, no change in voltage. But now we go through the light bulb, B to C. Now, if each of these light bulbs is identical, they're all going to use an equal share of the electric potential. So since we have 3 light bulbs, they're going to divide the 6 volts evenly amongst themselves. So we're going to drop down 2 volts. So from 6 to 4. And then from C to D, we have a good conducting wire, no change there. Then we're going to drop another third of our potential, another 2 volts from D to E. And then E to F, no change through a good conducting wire. And then through the last light bulb, right, we lose our last third of the electric potential, or 2 volts, and we get down to 0 at G. We'll have also 0 at H, and then back we go up to 6 volts as the battery increases the electric potential energy of our charge. All right, that's it. We have now defined electric potential difference, and we can calculate the potential difference from the work required to move a charge. Thanks for watching.